This is the video for lesson 9.1. Actually, there is only one lesson for 9, and it's kind of the review. This is the trapezium rule, or the trapezoid rule, if you prefer. As this is an AICE class, strictly we normally call this the trapezium rule. So what we're going to be doing in this unit is be able to use the trapezium rule to estimate the value of a definite integral, and be able to use a sketch in some cases to determine whether the trapezium rule is an overestimate or an underestimate of the actual area that we're trying to find. Now, when we did this originally in AICE 1, the idea of actually integration is that we're trying to find the area under a curve. What this picture is demonstrating here is, as we have more and more rectangles inside the shape, then what actually happens is the area of all these rectangles added together becomes very close to the area actually under the curve. Now you'll notice for some of these rectangles, the rectangle area goes above the curve, but you also notice it misses some of the area as well. And this basically balances out, and the more rectangles we put in, as you'll notice, we get closer and closer to the curve. So this is often referred to as a Riemann sum. And what we're actually doing here is, and I'm going to look at a picture that's not moving to make this a little bit easier to see, is we're trying to find the area by doing the sum of all the rectangles. Now for these rectangles here, the base of the rectangle times by the height, basically we want to make these rectangles as small as possible. So we try and make the width of these delta x. And the height of these ones is basically it's just the y-axis, so this is just the y value here. So we're doing the sum of all the rectangles. That's how you find the area of a rectangle. The base is delta x, and the height is y. And instead of writing a sum, I've just put s here. And I'm not sure if you all necessarily realize this, that the s is actually the origins for the integration symbol. It's the sum of, and then I use the commutative rule here to switch these two things around. Y times delta x. And y is another way of just writing f of x. And this is actually where our definition for integration comes from. What we're actually doing is we're doing a sum of an infinite number of rectangles. And when we do that, the more and more of these we get, the closer and closer it will be to the correct answer. And the smaller and smaller we make this width, the correct answer will become more and more close to what it should be. Now, that works pretty good for rectangles, but you could see from the picture here, there were some pretty big gaps here of white. In reality, it's actually even better, instead of using rectangles, if we actually use trapezoids or trapezium. Now, just to remind you, the definition for a trapezium is one pair of parallel sides. Normally you think of a trapezium probably twisted 90 degrees, but these are definitely trapezium. And we still have a little bit of a gap here, but certainly nowhere near as prevalent as what it was on that first picture that you saw. And this picture only uses two trapezium. So the trapezium rule is a good way of finding out an approximate area for a shape without actually having to do calculus, which is actually a really important skill. This is something we can program into a computer, and we can actually find the answer to integration questions without actually using calculus, just by finding the area of simple geometric shapes and adding them together. Now, to find the area of a trapezium, you need to know the two bases, which you'll notice here is actually just the y values, and you'll need to notice the width as well, which is actually in this case, or the height of the trapezium, which is actually the width in this case, which is actually just your x values. So as long as we know the width and we know the y values, which we can find obviously by substituting in the x values, we have a very easy method for actually finding the area by adding all the trapezium together. Now, I've started to answer a question here. What is the area under x squared plus 1 between x equals 0 and x equals 1? Now, they could ask the question in two ways. They could say with 5 trapezium, or they could say using 6 ordinates. So notice it's kind of like the word coordinates, but there's just one value for this. So in other words, we're talking about x values. So if you look at my picture here, here's between 0 and 1. This is the graph of x squared plus 1. You can see that part of that U-shape forming, and you can see the y-intercept of 1. Okay, if you count the trapezium, you can see 1, 2, 3, 4, 5. But if you look at the x values, you can see 1, 2, 3, 4, 5, 6. So by looking at this picture, what you should notice is here, if I plot the two y values and then join them together to make my trapezium, this is almost indistinguishable from the curve that you can see I've actually drawn here. This is just for 5 trapezium as well. So this is a very accurate method for actually finding out the area, but using a different method. So to find the height that I want to do is I have to look at basically what this distance is here. So 0 to 1 if it would be a distance of 1, so 1 take away 0 would tell us that. And then divide by the number of trapezium, so 5. If it says 6 ordinates, you've got to remember to subtract 1 to give you the number of trapezium. And that'll tell you what the width of each of these trapeziums is going to be, which will actually be the height when we come to work them out. Once we know our starting number, we can then count up by this height value here until we get to our final value, which is 1. And as you're doing that, you'll notice you get the 1, 2, 3, 4, 5. You'll get that 6 values, or those 6 ordinates that you talked about. Now, the clever part is, once again, we're not using calculus to do this. What we're actually doing is we're plugging x values into this formula here to find out what the y value is. Of course, this is something that computers can do naturally very quickly, just simple substitution. Now, the formula, rather than trying to work out each of these trapezium individually, there is a formula that basically does this very quickly for us. So the formula is 1/2 h y0 plus 2 times all the middle values and then plus the very last value. Now, the reason the middle values get times by 2, not that you really need to know, is this value here, notice it's part of this trapezium, but it's also part of this trapezium. So it gets used twice. And same for all the other ones in the middle. The only values that only get used once are the very end values, because it's part of this trapezium, but notice there isn't a trapezium here. Or on this side, there is a trapezium here, but there's not a trapezium here. And sometimes what will happen is you'll actually move this yn to the start. You'll add the first and the last value together, and then you'll do 2 times all the other values together added in. So once we're here, all this is now is this is a big substitution problem. So our width or height we found out was 0.2, so that goes in here for h. y0 is that first y value, which is supposed to be 1. Now, I actually changed this question and I failed to change my numbers in here, but that's fine. I can go back and change these as I go along. y1 is my first y value, so I'm filling those in. Then all my other y values, and I'm going to do this until I get to that very last value, and then actually I'm going to stop. So once I got to my next to last value, that's the end of this part here. And then yn is just your last y value, which is 2. And I'm going to need to fix these answers on the fly as well. Certainly 1/2 times 0.2 is 0.1. First and last values added together, 1 plus 2, that would be 3. And 2 times, if I add all these values together, I should get 5.2. He says, hopefully, please check on a calculator. And then if you work out all of this together, you should actually get the answer of 1.34. Please check on a calculator, but hopefully what you can see here is this is just a create a table by plugging numbers into this formula. Once you've figured out what the x values are, and then these values just go straight into this formula, and a lot of calculator work, but basically substitution to solve something that's an integration problem. Now, probably what's important for this, though, is right now, how good is this? Is this an accurate method? Well, let's try actually working it out properly, and this time I did actually do this correctly. So if I was to work out the integral of x squared plus 1 between those numbers, 1 and 0, then what I would find out is that it's x cubed over 3, increase the power by 1, divide by the new exponent. Integral of 1 is x, and then I would put those values between 1 and 0. So when I plug 1 in here, I would get 1/3, and obviously when I plug 1 in here, I would get 1. If I plug in 0 here, this is 0, and this is 0. So I got 1.33 as my answer, technically 1.33 repeating, but to 2 decimal places I got 1.33. And when I did this here, I actually ended up with an answer of 1.34. So actually the answers are really close together. And how could we have improved accuracy though? Well, if I go back to that original picture, notice the more and more shapes that I do, the closer the shapes become to the actual curve. I actually originally just started with 2, and you can see these little gaps here. Once I got to 5, you couldn't really see them because they're so small. So imagine if I did 10, 25, 50, 100. That's how you can improve your accuracy, depending on what level of accuracy you need. In most cases, probably 1.33 is going to be close enough. 1.34, that's probably going to be good enough in most cases. But if not, you can certainly increase the number of trapezium. Now, in terms of figuring out one of those other objectives, is it an overestimate or an underestimate? We kind of have to look at the picture. Sometimes you have to exaggerate these curves a little bit more so you can see exactly what's going on here. But as I look at the curve here, if I draw in 2 trapezoids and I put values at 3 points, As I join them up, notice that the area of the trapezoid is smaller than the area under the curve because I have this extra little piece here. So the area of the trapezoid is an underestimate for the actual area. Whereas on this side, if I join the points together, there's the area under the curve, but you can see actually we have a little extra piece in here. So this would be an overestimate. So that's also useful to know. If our answer is not 100% accurate, we want to know, is it a little bit too big or is it just a little bit too small? Now, at this point, I'm also going to remind you of something from a previous lesson because this will be useful on some of the questions. The integral of cotangent x, remember you can write cotangent as cosine over sine. And when we're doing integrals with fractions, what we're looking for is the top, the differential of the bottom. If it is, then we can write the answer as the ln of the bottom term. Of course, I should have plus c here as well. And on a similar idea, if you're doing this for tan x, that's sine over cosine. The differential of cosine is negative sine. So if I fix this question here, if I write negative sine x, but add an additional negative in here, the two negatives obviously would make a positive. Now, as I have the top as the differential of the bottom, I could write this question as the negative ln of the denominator, which is cosine x plus c. Now, the reason I'm throwing this one in is, just like we did our original question where we looked at how accurate was the actual question, of course, if the question's to do with tan x or to do with cotangent x, if you can't remember how to integrate that to check your answer, then that could be a potential problem. And that could apply for any question. So any of those trig integrals that we did, if they ask you a question with a trapezium rule and ask you to compare the answer to the original, it's really important that you know how to do that. And that's a good way of checking. Do you know the trapezium rule? And do you know your integrals as well at the same time? That'll conclude it for this video. There are some other older videos where I actually go through some actual questions. You could certainly find those on my YouTube channel as well if you need to.